Hello, my dear students. Welcome to my class Physics. Today's topic is work done by a constant and a variable force, nature of work. Let us what is the work? When it is said to be work done by a force. Work is said to be done whenever a force is applied on the body and the body moves through a certain distance in the direction of applied force. The point where force is applied is called as point of application. Hence, we can say that work is said to be done if the point of application moves in the direction of applied force. That means जब हम लोग force apply करते हैं, so in the direction of the applied force there must be some displacement in the same directions. But if the point of application of force does not move, that is no displacement in the direction of applied force, then work done is zero. That means there must be some displacement along the or in the same direction of applied force. At that time, it is said that work done by that force. Work done by a constant force. Initially, just we discuss about the work done by a constant force, and later on, and how can you find out the work done by variable force? हम last में हम लोग उसको बात करेंगे. Let's say constant force F acts on the body to discuss it. Here, two cases arises. When force acts along the direction of motion of body, that is in this figure diagram, let us see the position A of the body. At this position, force is applied here in this left to right directions. And after sometimes the position of the object is at point B, and there is a displacement along the same direction of the applied force. Let us say force F is applied on a body which is at rest at position A. Under the application of force, body moves through a distance S parallel to the line of action of force along the direction of applied force. Here, the work done W, that will be force into distance moved along the directions of force. That is, directly we can multiply here W is equal to F into S. But generally, it is not always occur. When we apply some force or some force is applied on an object, and always the object is moving along the same direction of the applied force. When it is not along the same direction of the applied force, that is when force acts some angle with the direction of motion of the body. Now let us suppose another example. Let us say constant force F is applied on a body such that the force makes an angle theta with the direction of motion of the body. That means here it is the direction of motion left to right, and it is the direction of the displacement also. And F is applied here, and there is an angle between the displacement and the applied force. In this case, the force, total force, it is not responsible for the displacement. Only one component, that is one fraction of the force, it is doing some work. In such a case, we have to take what component of the force, and that is acting along the same direction of the applied force. Now there are two components of this applied force. One is the F cos theta, that is along the same directions of the applied force, and let us suppose the displacement taken place along the x-axis. Therefore, we can say this F cos of theta, that is the Fx, that is the x component, and another component, that is F sin theta. Now we can say vertically upward direction, it is the Fy, and we consider here it is one horizontal plane. And after some time, the new position of the object will be here, and there is a displacement along the F cos theta. So when we resolving F into two components, we write here Fx is the Fx means we considering the object is moving along the x-axis. The Fx is the F cos of theta, that is horizontal component of force, acts along direction of motion of body. Another Fy, that is F sin theta, vertical component of force, acts perpendicular to the direction of motion of body. As the body moves along the direction of the component F cos of theta of force, then work done in displacing body through a displacement, that is work done, that is the component of the force in the direction of displacement into magnitude of displacement. That is, what is the effective fraction or effective part or effective component, that is F cos theta. This part or this component of force, it is doing work. And what is the work done? Now F cos theta into distance or displacement. Directly you can multiply now it F cos theta into S. That is Fs cos theta. And work, obviously it is a scalar quantity. Now force and displacement both are vector quantity. And we know Fs cos theta, that means we can write here F dot S. That means we can say anotherly, if we take the dot product of the force and displacement, then we can get the work done. Thus work done in is the dot or scalar product of force and displacement vectors. Hence work is a scalar quantity. Since the body has no motion along upward or downward directions, so no work is done by the component F sin theta. Here only F cos theta component is doing work, and in such a case we can write there is a Fs cos of theta into Fs cos of theta, and vectorically we can write it is F dot S. Result is the work, it is a scalar quantity. Therefore we get a dot product, or obviously Fs cos of theta, that is F dot S. Now, if we consider the displacement and also force in rectangular component forms, in case of three-dimensional, we can take the force. There are three components, and in three-dimensional case, generally we are taking a frame of reference x-axis, y-axis, and z-axis, and we know I cap, j cap, and k cap. These are the unit vectors along the x-axis, along the y-axis, and along the z-axis. Similarly, in three-dimensional cases, the displacement taken place, and that can be written in this way: xi cap plus yj cap and zk cap. That means if the force and displacement both are given in the rectangular component forms, then to find out the work done, we have to take the help of the dot product concept, that is W is equal to F vector dot S vector, and we can write the force in the form Fxi plus Fyj and plus Zk. These three are the x component, y component, and z component of the force. And the xi cap, it is the displacement along the x-axis, a component of the displacement along the x-axis, and yj cap, that is the component of the displacement along the y-axis, and zk cap, that is the component of the displacement along the k-axis, that means z-axis. Now taking the dot product, we know that I dot I is the 1, I dot j 0, and I dot k 0. Similarly, j dot j is the 1 and k dot k is the 1, and other dot products I dot k or j dot k, these are 0. Therefore directly we can write here fx x into fx plus y into fy plus z into fz, and it is general for formula. Obviously work is a scalar quantity and it has the magnitude only and no directions. Now some basic facts about the work. First of all, what will be the dimensional formula and what are the different units in different system of units. Work, now we know the work is the force into distance, that is W is equal to F into S, or Fs cos of theta. Cos theta is dimensionless quantity. Therefore dimensional formula of work, that will be the dimensional formula of F into S. And we know the dimensional formula of the F, that is the M L T minus 2, and for the S, that is nothing but one type of length, that is the L, and now we get M L to T minus 2. So dimensional formula of the work, that is the M L to T minus 2, that will be also the dimensional formula for the energy, and in future you will get one term torque. There also will be dimensional formula of the torque M L to T minus 2. Now units, and how can you find out the unit? Now by taking in this way, when F is the 1, S is the 1, at that time work done is the 1. In the different system of units, we define in this way: the unit of work is the amount of work done when a unit force displaces the body through unit distance in the direction of force. That means in this way you can remember it, when S is equal to 1, F is equal to 1, we can write in language that when a force is applied on an object of unit force is applied on an object, and there is a displacement of unit displacement in the same direction of the applied force, then work done is to be taken as the unit work done. Now work are two types, units of work are two types. One is the absolute unit of work, another gravitational unit of work. It is due to, we know there are two types of units of force. One is type of unit of force, absolute unit of force, and another gravitational unit of force. And when we use the absolute unit of force, the unit of work, that will be absolute unit of work. And when we consider the gravitational unit of force, at that time we will get a gravitational unit of work also. Now, first of all, what is the absolute unit of work? Work is said to be absolute unit of work if the absolute unit of force displaces the body through unit distance in the direction of applied force. That means here we consider the absolute unit of force. Obviously, at that time, the unit of work will be absolute unit of work. In SI system, we know the absolute unit of force is the Newton, then 1 Newton into 1 meter, that is 1 Newton meter. It is the unit of the work in SI system, and we know the 1 Newton meter also named in another way from the famous scientist Joule. We also say it is the Joule. That means 1 Joule is nothing but 1 Newton into meter. Work is said to be 1 joule if a force of 1 Newton displaces the body through 1 meter in the direction of the force. In CGS, absolute unit of a force is arg. How can you define it? We know the unit of it is not the force, it is unit of work, that will be arg. And we know that unit of force in CGS system, that is the 1 dyne. Therefore, 1 arg will be 1 dyne into centimeter or 1 dyne centimeter. There is no special name of the dynes. There is special name of the dyne centimeter, and that is the arg. So what is the arg? Work is said to be done 1 arg if a force of 1 dyne displaces the body through 1 centimeter in the direction of applied force. These two definitions are exactly similar definitions. Here we are saying that when 1 Newton force is applied on an object and there is a displacement 1 meter in the same direction of the applied force. Here similarly we are saying 1 arg is equal to when a force of 1 dyne applied on an object and there is a displacement of 1 centimeter in the direction of the applied force. That means these two are similar definitions, and there is a relationship obviously between the 1 joule and arg. 1 joule is the 1 Newton into 1 meter, and we know 1 Newton is the 10 to the power 5 dyne, and 1 meter is the 100 centimeter. Therefore, 1 joule, that will be 10 to the power 7 dyne into centimeter, and that is nothing but 10 to the power 7 arg. 1 Newton is the 10 to the power 7 dyne, and 1 joule is equal to 10 to the power 7 arg. I am telling again, joule is the unit of energy in absolute unit of energy in SI system, and arg is the absolute unit of energy in CGS system. Now, where gravitational unit of work. The work is said to be the gravitational unit of work if the gravitational unit of force displaces the body through unit distance in the direction of applied force. Obviously, when we are saying gravitational unit of work, then we have to take the gravitational unit of force also. In SI gravitational unit of work is kilogram meter. That means kg meter. We are saying it. It is, what is the 1 kg meter? Now, when one force of 1 kg weight is applied on an object and there is a displacement in the same direction of applied force is 1 meter, then it is kg weight into meter, and be careful about it. Weight is silent here, and when we write only kg meter, kg into meter, but it is kg weight into meter. But shortcut we write kg meter, and 1 kg weight meter or kg meter, that is equal to 9.8 Newton into 1 meter, that is 9.8 Newton meter or 9.8 joule, approximately 10 joule. That is one bigger unit. Gravitational unit of work is somehow bigger unit, and that is approximately 10 times of the joule. In a SI system, work is said to be 1 kilogram meter if a force of 1 kg weight displaces the body 1 meter in the direction of the applied force. We can define in this way. Just you write the 1 kilogram weight force is applied on an object, and there is a displacement in the same direction of the applied force 1 meter. Otherwise, you have to take cos of theta. If direction is not same, then for the definition we are taking in the same directions. In CGS gravitational unit, work is gram centimeter. Gram centimeter, obviously, it is a gram weight into 1 centimeter, and 1 gram weight, you know, that is 980 dyne into 1 centimeter. Therefore, 1 gram centimeter is nothing but 980 dyne into centimeter, that is 980 arg. So work is said to be 1 gram centimeter. Here also you just observe it, a gram weight centimeter, but when we write if we write gram centimeter weight or gram force into 1 centimeter, the force or weight that is just silent here, and we are saying that gram centimeter, and be careful about it. This is one confusing term, gram centimeter. Suddenly, if you say what is the gram centimeter, then you try to think it is nothing but the gram weight into centimeter, and that is nothing but the unit of work. Work is said to be 1 gram centimeter if a force of 1 gram weight displaces the body through the distance 1 centimeter in the direction of applied force. And similar definitions. So now we have know there are different types of unit of work, absolute unit in SI system, in CGS system, gravitational unit in CGS system, and MPS system. Now another very important fact about the work, nature of work. And nature of work means sometimes work it is a scalar quantity, though it is a scalar quantity, but we are considering positive work, even if negative work, and zero work. And when the work is said to be positive work by the force or negative work by the force or zero work done, let us know it. First of all, when we are saying the work done by a force, that is positive work. The work done by a force is positive if the force acting on the body has a component along the direction of displacement. That means there must be a component of the force or the whole force when acting along the directions of the displacement, then the work done by that force is said to be positive. That is, we know that is F, it is the not F, it is the W, it is miswritten. W is equal to F dot S, that is Fs cos of theta. When theta acute angle, that is greater than or equal to 0 and less than 90 degree, at that time cos of theta, that will be positive. Mathematically, we can also say when theta is 0 degree or less than 90 degree, that is acute angle, at that time their work done will be positive because cos of theta is positive. And at that time, practically, we get a component of the force along the x-axis. So theta is a 0 degree, W is equal to F into S into S cos of theta. So W is equal to Fs cos of 0 degree, that is F into S of. When theta is a 0 degree, we know the cos theta is maximum, and theta 0 degree means the applied force and the displacement, they are acting along the same directions. And at that time, cos theta is the maximum. That means we can say if the applied force and displacement both have the same directions, then the work done will be a maximum by that force. Now, what is the negative work done? The work done by a force is said to be negative if the force acting on the body has a component in the direction opposite to the direction of displacement, or as a whole, the force is acting opposite to the direction of the displacement, like frictional force that is always acting opposite to the direction of the displacement. This type of work done by forces are taken as a negative work done. Let us suppose here one example. One object is sliding through this inclined plane, but one force is applied, F, that is F applied to check or to slow down the speed of the object which is moving through the inclined plane. Now this F, that is applied force, but displacement is taken place in this way. The angle between the displacement and the applied force, this angle alpha, that is the obtuse angle. And when we take F dot S vector, that is Fs cos of alpha, here alpha is the obtuse angle greater than 90 degree, obviously cos of 90 greater than 90 degree, that will be negative. Mathematically, it will be negative. Otherwise, we can say the force, it has one component opposite to the direction of the displacement. Displacement from lower towards lower end, but F cos of theta, that is opposite to the direction of displacement. In this case, we are saying that this F work done by the force is negative work done. Otherwise, when the angle between the two displacement and the force, if it is obtuse angle, even if 180 degree, at that time work done by the force is negative. Now till now we are now see that work done by a force may be positive, may be negative. Now positive negative work done, one example, in the same case we can consider positive work done by the some force in the same event, and negative work done by the other forces. As for example, when one object is moving downwards, at that time the mg, that is the weight, that is nothing but a force that is acting downwards the displacement that is also along the downwards. Now we can say the work done by this weight or gravitational force is positive work done, because the displacement and the direction of the weight, that is force acting on the object, both are in the same direction. So work done obviously positive work done. But when this same object is lifted from upward directions by any external agency, let us suppose exactly F is equal to mg applied on it, and it is moving upwards. In such a case, the displacement that is along the direction of the applied force, so we can say the work done by the applied force is positive. But at the same time, at the same event, the displacement that is opposite to the weight, therefore at the same event we can say the work done by the weight, there is negative work done. And these are written here: when a body falls freely from certain height, work done by gravity is positive. Here theta is a 0 degree. Obviously, the displacement that is along the same direction, F W is equal to F dot S, that is mg h cos of 0 degree, that is mg h work done positive. But when a body is raised vertically upward from point A to point B through height h, here F equal to mg is, that is the weight of body, acts vertically downwards, whereas displacement is in upward directions. Therefore, W is equal to F dot S mgh cos of 180 degree, that is minus mgh. That means W is equal to minus mgh, that means work done is negative. And now, in the same event, when work done by the applied force is positive, when any applied force that raises an object against the gravitational force, at the same event, work done by the gravitational force is negative, because the gravitational force always acting downwards, but displacement is upward in directions. Now, when brakes are applied to move moving vehicles, then work done by the braking force is negative. All the frictional force that were done by the frictional force negative, because frictional force always acting opposite to the direction of the displacement. When a body is moved over rough horizontal surfaces, then work done against the frictional force, or but not against, work done by the frictional force. Here it should be not against, work done by the frictional force is negative. When a gas filled a cylinder fitted with frictionless piston allowed to expand, work done by the gas is positive. That means when expansion taken place, work done by the gas is positive, because here the force due to gaseous pressure and displacement acts in the same directions. When gas is compressed, the work done by gas is negative. That means in such a case, the force applied by the gas on the piston, and the displacement taken place in the piston in opposite in directions. Therefore, when any gas is compressed, work done by that gas is negative. But when the expansion taken place, the work done by the gas is positive. And there is one very important concept and widely used in thermodynamics. Now, zero work done. When the work done is said to be zero work done. Now, if the point of applications number one force does not move, no displacement in the direction of light force, at that time work done is zero. That means if you try to push the wall of your house or room, but there is no displacement, then work done by that applied force is zero. Work done by a force is zero if the force acts on a body in a direction perpendicular to the displacement of body. Here, the angle between the force and the displacement is 90 degree. That is F W equal to F dot S, Fs cos of theta, cos of 90 degree. So W equal to Fs cos of 90 degree, that is Fs into 0, that is the 0. That means when, if any displacement that is perpendicular to the applied force at that time, naturally work done by that force is 0. Maybe some other forces doing some work. As for example, when a coolie moves over a horizontal road with a weight on his head, does no work against gravity. Here, angle between the force and the displacement is 90 degree, and W equal to Fs cos of 90 degree, that is W equal to 0. This example should be clear to you. When the coolie take a load and moves in a horizontal platform, at that time the applied force on the load by the coolie, that is against the gravitational force, but the movement of the coolie, that is perpendicular to the gravitational force in the horizontal load. In such a case, that work done against the gravity is zero, but we are not so saying that work done by the coolie is zero, because somehow other forces acting simultaneously, some other forces doing some work, but work done against the gravity is zero. That should be clear. At the same event, there are several forces acting. When you push any wall other forces are also, you applied some force on the wall, but other forces simultaneously acting in action in your body. There is stretch and strain of the muscles, etc., etc. You can definitely say that the pushing force, when there is no displacement of the wall, the pushing force were done by the pushing force is zero, but were done by that person is not zero, because so other forces act in action at the same interval. Therefore, when you say the word done in any cases by zero, you have to mention the particular force. By that force, the work done is zero. In this example, pulley, that he is not work done against the gravity, but the pulley applied force against the gravity. But it should not you say that work done by the pulley is completely zero, because so many other forces at the same time in action during this walking of this, etc., etc. Now, tension in the string, we know that when a pendulum oscillates, the tension is always acting toward the center of oscillations or point of oscillations, and this is a point of suspension T tensions, and that tension T always perpendicular to the displacement at any moment. Tension T in the string of a simple pendulum, when it is oscillate, is always perpendicular to the displacement of bob. So work done by the tension is zero here, because the displacement is always perpendicular, that is tangential, but the tension, that force is acting toward the point of suspension, always the two are perpendicular, therefore work done by this tension is zero. Similarly, there is very important concept, that is work done by centripetal force always zero. We know that centripetal force acts in action when a body moves along a circular path, then the centripetal force always acts toward the center of circular path, whereas the displacement is tangent or along the tangential directions displacement. So always the force, that is the centripetal force, and the displacement, these are perpendicular, because we know the force acting along the radius and the displacement at any place, any point, that is along the tangent, and radius and tangent always perpendicular to each other. Therefore, the centripetal force and the displacement at any moment, and these are perpendicular to each other. Therefore, the angle between these two, 90 degree cos 90 0, that is work done by zero. In any situations, even maybe one electron is revolving around the nucleus, satellites are revolving around the planets, etc., etc. In anywhere, the centripetal force doing no work. That means it cannot do work, any type of work, because only the force and displacement are perpendicular to each other. Now, our next topics, in all the examples, we are considering the force throughout the whole displacement. In the different cases, already we have calculated in the above examples. We are taking the force or applied force or against force are constant in nature. But in our daily life, always the force not will be constant, rather than we are facing variable forces. Let us say variable force F act on a body, and let the body is displaced along the direction of applied force. The magnitude of force F depends on X as shown in the figure. That means at the different point, let us suppose the object is moving along the x-axis, and it is the initial point, is the final point, and there is a variation of the force. Gradually, force gradually increases, and the different way it is increases, at the different rate it is increases. So, in such a case, how can we find out the work done by this variable force? There are two methods to find out the work done in case of variable methods. One is the graphical method, by finding the area under the graph, that is also nothing but the total area under the graph, and graph, that is the displacement versus force graph. Area under the graph, that represents the total work done for the displacement this point to this point. Another way that is widely used, that is the calculus method. If we get there is a particular equations of the variation of the force with the distance, then we can find out also with the help of the calculus method. To calculate the work done by variable force, that is, let us suppose fx. X means it is a function of x. That means for the different value of x, the force will be different. That means at the different point, F will be different. To displace the body from initial positions xi to final positions xf, divide the total displacement into large number of thin sheets, each having thickness delta x. The displacement of thickness delta x is so small that the force Fx can be assumed as constant in that interval. That means if we consider the several intervals, several small displacement, and if delta x is very small, then we can consider the force or average force during this displacement remains unchanged. And at that time, for this very small displacement, we can write force into displacement directly. Now, force into displacement, it is the value of the force, and it is the displacement. It is nothing but the area, and we can consider it is a rectangular area, and then we can multiply delta x and fx. That is the area of the strip, and that is nothing but the work done dw for the very small displacement delta x. If fx bar be the average value of force in the interval delta is very small, and therefore it may be considered as a constant. Then the work done by the force over any interval, that will be dw delta w, that is the fx bar into delta s, that is the area of the strip. Area of the strip, this is area, that is nothing but area of the strip, having the height of f bar x and with delta x. Therefore, total work done by the force when the body is displaced from xi to xf, W is equal to, that is summation of all work done for the different small displacement delta x, delta x, delta x, delta x. Then we can get the summation, and that is nothing but the area of all strip between xi and fx. That means if we consider small strip, and area of this small strip is the work done during this displacement delta x. Similar way, we can find out this one plus this one. These are the nothing but area of these strips. Then what is the total work done? That is nothing but the area of the whole strip, and that is nothing but the area under this graph, under the force and displacement graph. And this one, and if we take this delta x tends to 0, and number of strips become infinity, in such a case we can take the symbol of the integration, and at that time we can write x limit of the x is the xi to xf fx dx. That means when the delta x tends to 0, we consider very small and infinite number of large number of strips, then area under the curve between xi and xf, that will be nothing but the integration of fx dx by taking the limit, lower limit is the xi initial I and xf final f. So work done, ultimately we get area under the force versus displacement curve, and otherwise we can take the help of the integration. In these two way, we can find out the work done by a variable force. And this concept will be clear by the two examples. Let us suppose and there is a definite variations or relationship of the variation of the force with x. A particle moves along the x-axis from x equal to 0 to x equal to 4 under the action of force given by F equal to 5 minus 7x plus 4x square Newton. That means it is given in the SI system. What will be the work done in this process? And obviously x is also taken in the meter. Then here the F is the 5 minus 7x plus 4x square. That means it is a function of the x for the different value of the x. That means at the different point F will be different. Now work done by variable force, the starting point is x is equal to 0 and final point x is equal to 4. What how can you find out the work done? In this type of questions, we have to take the help of the integration or method of calculus. Now this method is very simple method. Force is this and displacement is this. For very small displacement, let us suppose f ds or f dx. In this case, we are taking along the x-axis, therefore we are writing that f dx and integration xi, that is the 0 to x f xf is the 4, then 5 minus 7x plus 4x square into dx. And by distributing these one, that is the 5 0 to 4 5 dx minus 7x dx plus 0 to 4 4x square dx. Now this is we know the 5 is the constant, and the integration dx is the x, integration 7 constant, integration x dx, that is the x square by 2, because x power 1 plus 1 divided by 1 plus 1, that is the 2, that is 7x square by 2, and it is the 4 x square dx, that means 4x cube by 3, and in all cases lower limit is 0, upper limit is the 4. Now by putting the lower upper limit minus lower limit in this way, that is 5 into 4 minus 0, 7 by minus 7 by 2 into 4 square minus 0 square plus 4 by 3 into 4 cube minus 0 cube. And from that we get 5 into 4, and that is a 7 by 2 into 16 plus here 4 by 3 into 64, and that is a 20 minus 56 plus 256 by 3, and ultimately we get 49.3 joule work. Now in this case, when the force is variable, then we can take the help of, and the variable variations of the force, if the function of the displacement and any relationship is given, then in this way we can solve the problems, we can find out the problems. But sometimes if we take the graphical method, some questions also can be solved in graphical method. One example, a woman pushes a trunk on a railway platform which has a rough surface. That means she has to push the trunk against the frictional force. She applies a force of 100 Newton over a distance 10 meter, and thereafter she gets progressively tired, and her applied force reduces linearly with the distance of 50 Newton. The total distance through which the trunk has moved is 20 meter. Plot the force applied by the woman and the frictional force, which is 50 Newton, against the distance. Calculate the work done by the two forces over 20 meters. First of all, you just read the questions 2 times and then try to draw the graph. And if we draw the graph, we are saying here, this given here, for the first 10-meter displacement against the friction, the force applied, that is 100 Newton. And after that, and thereafter, she gets progressively tired. That means the applied force gradually decreases, and up next 10 meters, the force gradually decreases from 100 Newton to 50 Newton, and there is a total displacement is that 20 meter. Then what is the work done by that applied force, and what is the work done by the friction force? There are two types of force. One is the friction force. Work done by applied force, that is the W1, let us suppose. That is area of the rectangle plus area of the trapezium. Area of the rectangle जो है, area of the rectangle, that is the, this is the 100 and it is the 10, that is 100 into 10 plus area of the trapezium BDEC, that is half into sum of these two parallel sides into distance between these two. That is W1 is the OA into OD, OA into OD plus half into BD plus CE into DE, that is the perpendicular distance, and the value of the DE is the 10, and it is the 10, it is the 100, and it is the 100, and it is the 50. By putting all these values, we can easily find out the work done. That means it is one easier method to find out the work done by graphical method. If we get such variations, and if we can draw the graph displacement versus force. Now work done the frictional force, but throughout the whole path, the frictional force, that is 50 Newton, and that remains constant. That means what is the work done by the frictional force throughout the whole path of the displacement, that is 20 meters, the frictional force remain unchanged, and in this case it is area. And here we can take some negative sign because the work done by the frictional force is -1, because the displacement and the force, these are opposite in directions. So work done, that is the W2, that is minus into area of the rectangle, and this area of the rectangle is the 50 into 20, that is 100 joule. That means work done by the applied force or by that woman, that is 750 joule. But at the same time, work done by by the frictional force, that is minus 1000 joule. Now it is the end of this lesson, and we'll further meet with you with the second lessons.